We're going to use basic physics to come up with an expression for the pressure. So imagine that we're given a particle experiencing elastic collisions with the side of some box. So here's the box, and what I mean is that the particle's in there and it's just going back and forth within the box, and an elastic collision tells you that the magnitude of the momentum is conserved as it bounces. So it's not like this thing is dissipating a lot of energy every time it hits the box. Let's say that the particle has a mass m part and an x velocity vx, we'll worry about velocity details in a little bit, and get started. So if we want to construct the pressure, well, we know from early in the course that pressure is just an average force per area, so what you can imagine is you have this particle and a bunch of other particles like it all hitting the sides of the box. That's what's causing gas pressure. So what we want to do is just construct this average force F sub x with the bar over it, where the bar tells you I'm talking about an average. And the area in this case would be the area of the side of the box where the particles are hitting. Okay. So how can we relate this force to what the particle is doing? Well, if you remember from intro physics a long time ago, you may have learned about the impulse momentum theorem, which tells you that the average force over some time interval, ends up being the change in a particle's momentum. Now, what you can imagine is that if we're considering the point of view of the side of the box, then if the box were free to move, if it were a piston without friction or something like that, then it would experience the same change in momentum of the particle every time that a particle hit it, because of course momentum is conserved. So what you can imagine is we're describing the change in momentum of one of the walls if there were not a restoring force to keep the wall in place. And all that says is that the average force times delta t will be the change in momentum, which for a fixed particle mass is just going to be m times the change in x velocity. Now, for elastic collisions, we actually know how to evaluate this change in velocity, right? Because it goes in and comes out with the same speed, but the direction has been reversed. So the change in velocity is not zero. The change in velocity is actually twice whatever the initial speed was. So if we assume that the initial speed was positive, then we can just say that the average fx times delta t equals the mass of the particle times 2 vx. Now what do we do with that time factor? Well, again, if we're considering the point of view of one of the walls, how often does this happen? It experiences a collision every time the particle goes back and forth within the box, and that takes a total time interval of 2 times the length of the box divided by the particle's velocity. So that's how often it gets hit by a single particle. We can substitute that expression back into our expression involving the average force to see that Fx average times 2L over Vx equals 2m Vx. The 2's will cancel, and we can multiply both sides by Vx to find that the average force is mVx squared over L. Okay, let's keep that result. Now, if we want to rearrange that for the pressure, remember the pressure was the average force per area, so all we did was divide that Fx expression by area. But now you notice in the denominator I have the length times an area. For rectangular solid, that's just going to give you the volume, right? So L times A is the volume. That means for each particle that the pressure is mVx squared over big V, which is now the volume in the denominator. So remember, V with ears is velocity, V without ears is volume. Okay, so that's per particle. If we wanted the total pressure, then we can imagine that this is happening with a bunch of particles in a box all at once, and we would find that the pressure is just big N, the number of particles, times mVx squared over V. Now it's a little funny to imagine that all the particles are moving perfectly horizontally so that they only have x velocities. What happens in real life, of course, is that they have nearly random velocities in a bunch of different directions in 3 dimensions, so we ought to account for that. In 3D, the full average velocity squared is going to be a combination of Vx squared plus Vy squared plus Vz squared. Assuming that they really are random velocities, so that Vx squared would be equal to Vy squared on average would be equal to Vz squared, then we would say that just the Vx average squared would be 1/3 of the total velocity squared average. So we can go through, keep that, and actually plug that into our relationship for the pressure. So the pressure should be on average number of particles times their mass, times now we've constructed the average of total V squared, not just Vx, divided by 3 times the volume. So that's the pressure. Now what happens if we insert this into the ideal gas law? Well, let's pick the form that P big V equals little n R bar T, where little n in this case, just to be clear, is the number of moles. We can substitute in our expression for P, so we do that. We'll keep that up there. Now we can multiply both sides by 3 and cancel out those factors of volume to see that n times mv squared average equals 3 little n R bar T. Well, actually, what happens now if we multiply both sides by 1/2? We have n times 1/2 mv squared equals 3/2 n R bar T. You may recognize what's going on the left-hand side. We'll isolate it. 1 half mv squared average equals now 3 halves this weird combination little n over big N r bar t. There's a couple things we notice. One is that 1 half mv squared average is just the average kinetic energy of particles. Cool. Another thing maybe you didn't notice was that little n over big N times r bar is equal to r bar divided by Avogadro's number. Maybe you haven't thought about that number much since chemistry. Put in the values though, and that's equal to the Boltzmann constant. There is a relationship between Kb and r bar. We should have suspected it all along, but now we know it. So we can substitute both of those expressions in to our expression up there for 1 half mv squared and find that the average kinetic energy is just 3 halves kT. So if you know the temperature of an ideal gas, you immediately know the average kinetic energy of its particles. Furthermore, you can compute its internal energy because it turns out that the internal energy is just going to be the sum of all this average kinetic energy for all of these particles. So really all we have to do to compute the internal energy is to multiply the average kinetic energy by the number of particles n. If we substitute in the expression for the average kinetic energy that we just got, then U becomes 3 halves nkt. Now, strictly speaking, this expression only holds for a monatomic ideal gas. You would not want to apply it to a really complicated set of molecules, and particularly not to something that's not a gas, because there you can have other forms that the internal energy can take. But for a monatomic ideal gas, that's your average kinetic energy, that's your internal energy.